So today we are going to start a new chapter entitled Laplace Transform. Laplace transform of a function ft is given by integral 0 to infinity e to the power minus pt ft dt where t is strictly greater than 0. I'll again repeat the definition. Laplace transform of a function ft is given by 0 to infinity e to the power minus pt ft dt. Here L is known as Laplace transformation operator. Now in some books you'll find that instead of using P, they are using S. So I've written here some authors use the letter S in place of P. Now there is one property which is known as linearity property of Laplace transform. Now this property says that L of C1 F1t plus C2 F2t is equal to C1 of L of F1t plus C2 L of F2t. Now Laplace transform of some elementary functions. Here it should be F2t, okay? I've written Ft but it should be F2. Alright. Now Laplace transform of some elementary functions. To prove that L of 1, Laplace transform of 1 is equal to 1 upon P where P is positive. Now we know the definition. What is definition? L of ft is 0 to infinity e raised to minus pt ft dt. Now in place of ft we write here 1 because we have to find the Laplace transform of 1. So L of 1 will be 0 to infinity e to the power minus pt into dt because ft is 1. So integration of this is e raised to minus pt upon minus p. Limits are from 0 to infinity. And then you put the upper limit. What will be e to the power minus infinity? E to the power minus infinity is 0. And e to the power 0 is 1. So we have 0 minus 1 upon t. This comes out to be 1 upon. So Laplace transform of 1 is 1 upon t. Alright. Next we find out Laplace transform of t raised to the power n. Now Laplace transform of t to the power n is gamma n plus 1 upon p to the power n plus 1. Conditions on p and r, p should be positive and n should be greater than minus 1 because then only the gamma function will be defined. Okay, so let's start with the definition. L of t to the power n. By definition this is 0 to infinity e raised to the power minus pt t raised to the power n pt. Now put p into t is equal to x. If we differentiate it with respect to x, so what do we get? P into dt by dx is equal to dx. So therefore dt is equal to dx upon p. So substitute this here. So L of t to the power n is 0 to infinity because limits for x will again be from 0 to infinity. E raised to the power minus x. In place of t we put x upon p. So this is x upon p to the power n. And in place of dt we write dx upon p, which is equal to 1 upon p to the power n plus 1, 0 to infinity e to the power minus x, x into the power n dx. X to the power n can be written as x to the power n plus 1 minus 1 dx. So this is the formula for gamma of n plus 1. So this comes out to be gamma n plus 1 upon p raised to the power n plus 1. Provided n is greater than minus 1. And we know that gamma n plus 1 is nothing but factorial of n. So this is factorial n upon p to the power n plus 1. So Laplace transform of p to the power n is factorial n divided by p to the power n plus 1. Next we find out Laplace transform of e to the power at. We show that Laplace transform e to the power at is 1 upon p minus a. P is greater than a. So by definition L of e to the power at is 0 to infinity e to the power minus pt e to the power at dt, which is 0 to infinity e to the power minus of p minus a into p dt. Now integrate it. We have e to the power minus p minus at upon minus p minus a. Limits from 0 to infinity. Again if you put the upper limit e to the power minus infinity is 0 minus 1 upon p minus a. So this is equal to 1 upon a minus t. So Laplace transform of e to the power at is 1 upon a minus t. Next we prove if t is positive, then Laplace transform of cos at is p upon t square plus a square, and Laplace transform of sin at is a upon t square plus a square. Let's start with L of cos at. By definition, L of cos at is equal to 0 to infinity e to the power minus pt cos at dt. Now we integrate it by parts. First function, second function. So e to the power minus pt into integral of cos at. Integral of cos at is sin at upon a. Limits from 0 to infinity minus integral 0 to infinity. Then differential of first function. The differential of this is minus p e to the power minus pt into integral of cos at, which is sin at upon a into pt, which is equal to 1 upon a limit t tending to infinity e to the power minus pt sin at minus, if you put limits of lower limit of t 0, so this is nothing, e to the power 0 is 1 and sin 0 is 0, so this is 0, plus p upon a 0 to infinity e to the power minus pt sin at dt, which is equal to 1 upon a into 0, this is 0, plus p upon a, now what is this? This is nothing but L of sin at. That means L of cos at, if we are taking on the left hand side, is equal to p upon a into L of sin at. So suppose this is equation number 1. Now we will find out L of sin at again by making use of integration by parts. So L of sin at is 0 to infinity e to the power minus pt sin at dt, again integrated by parts. This is equal to e to the power minus pt. Integration of sin at is minus cos at upon a. Limits are from 0 to infinity minus integral 0 to infinity. Differential of e to the power minus pt is minus p into e to the power minus pt. And integration of sin at is minus cos at upon a into dt. Again you put upper limit, lower limit, so this is minus 1 upon a 0 minus 1 minus p upon a L of cos at. See, so which is equal to 1 upon a minus p upon a L of cos at. This is equation number 2. So therefore we make use of equation number 1. Left hand side is same, L of cos at is equal to p upon a, and in place of L of sin at, we substitute this whole thing, 1 upon a minus p upon a L of cos at. So we take this L of cos at on this side, so we have 1 plus p square upon a square. L of cos at is equal to p upon a square. On simplification we will get L of cos at is equal to p upon p square plus a square. So therefore if we put it in equation number 2, so we shall have L of sin at is equal to 1 upon a minus p upon a into L of cos at. L of cos at we have found 3 upon p square plus a square. 1 upon a taken common, so we have inside the bracket 1 minus p square upon p square plus a square. To simplify it, we will get it as a upon p square plus a square. So therefore Laplace transform of sin at is a upon p square plus a square. Next we find out Laplace transform of hyperbolic function. Let's take Laplace transform of cos hyperbolic at. We should show that L of cos hyperbolic at is p upon p square minus a square if p is greater than mod of 2. Now we have found out L of e to the power at is equal to 1 upon p minus a. So therefore L of cos hyperbolic at is e to the power at plus e to the power minus at divided by 2. So by linearity property, we write it as 1 by 2 L e to the power at plus 1 upon 2 L e to the power minus at. Now Laplace transform e to the power at is 1 upon p minus a. Laplace transform e to the power minus at is 1 upon p plus a. To simplify it, we will get it as p upon p square minus a square is the mod of it. Similarly, Laplace transform sin hyperbolic at is equal to a upon p square minus a square. How Just make use of this formula. Sine hyperbolic AT is e to the power AT minus e to the power minus AT upon 2. Again make use of linearity property. So this is equal to 1 by 2 L of e to the power AT minus 1 by 2 L of e to the power minus AT. L of e to the power AT is 1 upon t minus a. L of e to the power minus AT is 1 upon t plus a. So simplify it, this comes out to be a upon t square minus a square, provided t is greater than a. So what we have studied today, you remember all this formulae, because we'll be reading all these formulas throughout the class. L of 1 is 1 upon p. These are the conditions for t. Laplace transform of t to the power n is gamma n plus 1 upon p to the power n plus 1, which is equal to factorial n upon p to the power n plus 1. Now in this, if you put n is equal to 1, we have L of t is equal to 1 upon p square. Laplace transform of p to the power at is 1 upon p minus a. Laplace transform of cos ad is p upon p square plus a square. Laplace transform of sin ad is a upon p square plus a square. Laplace transform of cos hyperbolic at is p upon p square minus a square. And Laplace transform of sin hyperbolic at is a upon p square minus a square. So these are the formulae we'll be using in this chapter. So remember all these formulae. And the next lecture we shall take few problems for finding out Laplace transform of various functions.